Hello everyone, Mr. Fawcett here, and we are back with another AP Calculus lesson. Today we're going to focus on solving differential equations. So in our previous lesson, we were given a solution and we were just asked to verify whether it was a solution or not. Now we're going to actually have to come up with those solutions on our own. So quickly, just to reiterate, a differential equation is an equation that relates the original function to one or more of its derivatives. And the equations that we solve in this class, we're only going to be relating it to its first derivative, but the more complicated differential equations you get into, you can have, an original function, its first derivative, its second derivative, all in the same equation. It just can make it more difficult to solve. We also know that the solutions to differential equations are going to be functions, not just numbers. So we're not going to get something like x equals 8 as a solution to the differential equation. We'll get something like y is equal to 4x squared minus 3, or y is equal to e to the x, or something like that. So our solutions are going to be functions rather than just individual numbers. Let's just jump right in. Our examples will get more complicated as we move on, so buckle in. This generally can be one of the tougher lessons that we cover in this course. Okay, so it says given below are differential equations with given initial condition values. Find the particular solutions for each differential equation. So we're actually going to do two things. We're going to find the general solution, and then I'm going to show you the difference between a general solution and the particular solution based on the given initial condition. Okay. When we are solving a differential equation, we're going to try to get the same variable on each side, right? So notice I have a dy and a dx here. Well, I'm going to try to get all the y's with my dy and all of the x's with my dx. Then I can integrate both sides with respect to their given variables. So in this case, the way to do that is to multiply both sides by dx, right? And I'm actually just going to cross this out because I may need to use the whole page. So if I multiply, and I'm going to start up here just for what it's worth. If I multiply both sides by dx, I get dy is equal to the quantity 6x squared plus 6x plus 2 times dx. Now, I can integrate both sides with respect to their given variable. The left side I will integrate with respect to y because I have a dy over there. The right side I will integrate with respect to x because I have a dy or I have a dx on that side. So I'm going to integrate both sides. Again, we're just taking the indefinite integral. So on the left-hand side, well, remember that there's just really a 1 in front of this dy. So the antiderivative of 1 would just be y. And you could put a plus c here. Okay. We're going to talk about whether we need that or not in a second, but we'll leave it there for now. On the right-hand side, I'm going to get 2x cubed plus 3x squared plus 2x. And again, I need a constant of integration, but I can't use c because they may not be the same. So let's just call this d. Now, here's the thing. I have two constants of integration, and they could be the same, they could be different. I don't need to represent both of them with a variable, though, right? Because think about it. What if I just subtracted c from both sides? Well, if I do that, I end up getting y is equal to 2x cubed plus 3x squared plus 2x plus some constant, right? It may not be c or d, so we could just call that, we'll just call it m for another name for a constant. So even though you have a constant of integration on both sides, if you move one of the constants to the other side, you can just represent both of those with one constant. And so, well, what we're going to do here is we're going to not put the constant of integration on our side with y. We're just going to leave it on our side with the x's. and thus we're just going to call it C. So we're going to call it C, and we're going to be done with it. And again, we just have to understand that that constant C is actually made up of both the constant of integration from the left-hand side as well as the constant of integration from the right-hand side. Okay, so here is my general solution, right? This is one solution. Well, actually, this encompasses all the solutions to this differential equation. So right here, we call this the general solution, because based on what that C value is, this function could be an infinite number of things, right? If the C was 1, that's a different function than if the C is -1. Now, they're saying we need to find the particular solution when f of -1 is equal to +2. So they're saying this right here works for this particular solution. Well, what that means is we need to go ahead and figure out what the C value would be to make that true, what I boxed in red. So let's take this again. F of -1. Well, you got to think about which of those represents the y value. Well, 2 represents the y value. -1 will be my x value. So I get 2 is equal to 2 times -1 cubed plus 3 times -1 squared plus 2 times -1 plus c. So I get 2 is equal to -2 plus 3 minus 2 plus c. That gives me 2. If I simplify the left-hand side, that gives me -1 plus c. And then I get 3 is equal to c. So to make what I boxed in red true, my constant of integration would have to be c, which means my particular solution is y is equal to 2x cubed plus 3x squared plus 2x plus 3. That is my particular solution, given this initial condition. So when you solve a differential equation, you can come up with a general solution, right, which can change based on what that constant is. Or they may give you an initial condition, which you can then use to find the specific or the particular solution based off of that condition. Okay, so I know the calculus portion of this was fairly straightforward as far as the integration goes. If you look at number 2, right, it gets a little bit more difficult as far as the integrating goes. But the process is going to be the same as far as how to find the general and the particular solutions. Let's go ahead and look at a different one. I believe we're just going to be doing the left-hand columns today. Yep. So we're going to do number 3. Let me cross out number 4. We won't do that one on video. So for number 3, you'll notice that we actually have some y's in our problem as well, or specifically one y. So again, like I said, our goal is to get the y's next to the dy's and the x's next to the dx. Well, actually the easiest way to do this would just be to cross multiply here. You could do it in steps, or you could just do it in one cross multiplication step. But that would give us 2y dy is equal to x squared plus 2x dx. Now I'm ready to integrate because I have my y's next to my dy, my x's next to my dx. So integrate both sides. Antiderivative of 2y is just y squared. Remember, I'm going to just keep my constant of integration. I'm going to only put that on the right-hand side with my x's. The antiderivative of the right-hand side would be 1/3 x cubed plus x squared plus c. So this equation right here would be considered the general solution to the differential equation up above. If you wanted to, you could actually solve for y, and you could get y is equal to plus or minus the square root of everything we have on the right-hand side. But we actually need to go further anyway, right? Because we're told that we have this initial condition right here, that f of 0 is equal to 2, or when x is equal to 0, y is equal to 2. So we need to go ahead and use that to figure out what our c is. So y is equal to 2 when x is equal to 0. And I pretty quickly figure out that c is equal to 4. So I'm going to rewrite my equation. I get y squared is equal to 1/3 x cubed plus x squared plus 4. So you may think, well, I'm done here, right? I figured out what my constant is, so I'm good to go. Well, not quite. There's still one more thing we have to do. Here, if I think about this equation right here, when I substitute in 0 for x, yes, y could be equal to 2, but y could also be equal to -2, right? Because if I substitute in -2 for y and 0 for x, that's also going to give me something that is true. So our initial condition says that when x is equal to 0, y is equal to 2. It doesn't say that when x is equal to 0, y is equal to positive 2 and -2. So what we have to do here is we actually have to solve for y. So take the square root of both sides, and we get y is equal to the positive and negative square root of 1/3 x cubed plus x squared plus 4. And now we need to think, should our answer be the positive square root or should it be the negative square root? Well, when I substitute in 0 for x, if I have the positive square root, I'm going to get y is equal to the square root of 4. Y is equal to 2, which is what I want based on my initial condition. If I do the negative root, so if I have y is equal to the negative square root of 1/3 x cubed plus x squared plus 4, when x is equal to 0, I get y is equal to negative the square root of 0 plus 0 plus 4. Y is equal to the negative square root of 4, so y is equal to -2, which is not what I want. So our final answer here needs to be just the positive square root. So y is equal to the square root of 1/3 x cubed plus x squared plus 4. This is our solution. So if you have a y squared, or you haven't solved for y yet, you need to do that because you may have to eliminate certain solutions that don't fit the initial condition. Okay, let's move on. Let's do one or two more. All right, this is a good one. Again, we're going to be doing number 5. And I'd encourage you to pause the video here. I think you've learned enough at this point to be able to make at least a good effort with number 5 and see if you can come up with that particular solution. Okay, so the first thing I'm going to do is separate my variables. I'm going to get my x's with my dx, my y's with my dy. So when I do that, I'm going to multiply both sides by dx and divide both sides by y minus 2. So I end up getting 1 over y minus 2 dy is equal to x to the power of 4 dx. And again, if you're confused about how to do that, just do it step by step. Now I'm going to integrate both sides. The antiderivative of 1 over y minus 2 is going to be the natural log of the absolute value of y minus 2. You need those absolute value signs so that it works for negative values of y as well, or rather when this quantity right here, y minus 2, is negative. On the right-hand side, we end up getting 1/5 x to the power of 5 plus c. So again, general solution right here, but we need to find the particular solution, so we have to go a step further. Well, it says that when f of 0, or it says when x is equal to 0, essentially, y is equal to 0, or f of 0 is equal to 0. So I should substitute in 0 for both x and y. I get the natural log of absolute value of 0 minus 2 is equal to 1/5 times 0 to the power of 5 plus c. This gives me the natural log of positive 2, right, because the absolute value of negative 2 would be positive, is equal to c. So c is equal to the natural log of 2. Well, let's go ahead and substitute that back into our general solution. So I get natural log of the absolute value of y minus 2 is equal to 1/5 x to the power of 5 plus the natural log of 2. Now you may be tempted to leave it like this, but you really need to get y by itself, because there may be some solutions that you do not want to use based on our initial condition. Well, how am I gonna get the y by itself here? Well, essentially we want to undo the natural log on the left-hand side. And to do that, we need to e both sides. Just like that. So what this will do, this will leave me with just y minus 2 on the left-hand side. And then I get e, whoops. Then I get e to the power of 1/5 x to the power of 5 plus the natural log of 2. This still may look confusing. Oops, I still need my absolute value signs here. One thing you could do to simplify this a little more, let me just do this up here on the right. I could break my e expression up, right? So thinking about exponent rules, this is equal to e to the power of 1/5 x to the power of 5 times e to the power of the natural log of 2. Again, just exponent rules. If you think about going in reverse order, right, if I'm multiplying two expressions that have the same base, I would just add their exponents. So I could do the reverse process as well. This is nice because this quantity right here, that just becomes 2. Right, so this simplifies to 2 times e to the power of 1/5 x to the power of 5. Just makes it a little nicer for you because we still have some more steps. So I'm going to come up here, and I'm going to get the absolute value of y minus 2 is equal to 2 times e to the power of 1/5 x to the power of 5. Now, to undo the absolute value, right, I'm going to get a positive negative quantity on the other side. So I can have either y minus 2 is equal to positive 2 times e to the power of 1/5 x to the power of 5, or I can have y minus 2 is equal to, I'm going to get rid of this. You probably already have that written down anyway. I can get y minus 2 is equal to negative 2 times e to the power of 1/5 x to the power of 5. So both of those work. You could think about it, like if I have the absolute value of x is equal to 4, that's equal to x equals positive 4, or x equals negative 4. Both of those would be solutions. So when I simplify these, or not simplify, but do my last inverse operation, I get y is equal to 2 times e to the power of 1/5 x to the power of 5 plus 2, or y is equal to negative 2 times e to the power of 1/5 x to the power of 5 plus 2. So I have two possible solutions, and I need to figure out which of those actually works with the initial condition, where if I substitute in 0 for x, I also get 0 for y. Well, if you think about this one on the left, If I substitute in 0 for x, I get y is equal to 2 times e to the power of 0 plus 2. This gives me y is equal to 2 plus 2, which is equal to 4. So that doesn't work, right? This solution does not work with our initial condition. Let's check to make sure the other one does. When I substitute in 0 for x, I get negative 2 times e to the power of 0 plus 2. This gives me y is equal to negative 2 plus 2, which gives me 0, which is what I want. I need y to be equal to 0. So this right here is our particular solution. Okay, like I said, these can get intense. You got to remember a bunch of different algebra rules. You had to understand the relationship between the natural log and the natural exponential function here, as well as different absolute value rules, etc. Let's see if I want to do one more. And we are going to do number 6. But again, I really want to see if you can do this entire thing on your own. So pause the video, use your notes for number 5 to help, and see if you can make it all the way through number 6 and come up with that particular solution. Okay, so here, when I rewrite this and separate my variables, and I'm actually going to start this over here just so I can work left to right, I'm going to get 1 over y minus 1 times dy is equal to 1 over x squared times dx. Now I'm going to integrate both sides. It may help to rewrite the right-hand side. So you can more easily use the reverse power rule. This would just be x to the power of negative 2 dx. If I integrate the left-hand side, I'm again going to get the natural log of the absolute value of y minus 1. Is equal to negative x to the power of negative 1 plus c. And now I can just rewrite that without the negative exponent. So natural log of the absolute value of y minus 1 is equal to negative 1 over x plus c. So again, there's our general solution. Let's use our initial condition that says f of 2 is equal to 0. So when x is equal to 2, y should be equal to 0. So I get the natural log of 0 minus 1. The absolute value of that is equal to negative 1 over 2 plus c. This gives me the natural log of 1 is equal to negative 1/2 plus c. Natural log of 1 is just 0. Makes it a little bit easier for us here. And I just get c is equal to 1/2. So I'm going to replace my c with 1/2 and rewrite this. Natural log of the absolute value of y minus 1 is equal to negative 1 over x plus 1/2. Now, again, I still need to get the y by itself because I may have to eliminate a solution if it doesn't work with our initial condition. So I'm going to e both sides, just like my last problem. So that's going to give me the absolute value of y minus 1 is equal to e to the power of negative 1 over x plus 1 over 2. Now, there's no other natural logs to simplify the e with, so we can just leave that e expression alone. What I do need to do is take both the positive and the negative of the right-hand side, though, so I can get y minus 1 is equal to positive e to the power of negative 1 over x plus 1/2. This is still going to be tight. Or I get y minus 1 is equal to negative e to the power of negative 1 over x plus 1/2. Now I need to see which of these work, or let me do my final inverse operation first, actually. So which of these work with our initial condition? When I substitute in 2 for x, I need to get 0 for y. Well, let's try it with the blue. So I get y is equal to e to the power of negative 1 over 2 plus a half plus 1. This gives me y is equal to e to the power of 0 plus 1. This gives me y is equal to 1 plus 1, which is equal to 2. That is not what I want, though. I want y is equal to 0. So this is no good. Hopefully the brown works. I'm going to get y is equal to negative e to the power of negative 1 over 2, or negative 1/2 plus 1/2 plus 1. This gives me y is equal to negative e to the power of 0 plus 1. Y is equal to negative 1 plus 1, which is equal to 0. So this right here is our particular solution. I don't have room to write that, but that would be our answer, the one in brown. Okay, the last two we did, 5 and 6, about as tough as they'll get in this class as far as separating variables and finding particular solutions. If you are not proficient, or if you have questions about the relationships between natural log and e, that's something we need to figure out, because it is going to pop up in this unit, pop up in exams, could pop up in the AP exam. And you don't want to not be able to answer a calculus question because we don't understand something from Algebra 2 or pre-calculus. So make sure we understand those relationships, and these equations will seem a bit easier when we are manipulating them. All right, that will do it for today. When I see you next time, we will start talking about something called a slope field. Enjoy the rest of your day, and we'll see you next time.